Testing. Good morning, everyone. How are we all doing?
Great.
Awesome. Aviation Club is happy to present Robert Stewart. Robert Stewart was born in 1942 in Washington, D.C. He acquired a bachelor's in science from the University of Southern Mississippi and later a master's in aerospace engineering from the University of Texas at Arlington. In 1964, he joined the United States Army and became a helicopter pilot, logging over 1,000 hours of combat time in Vietnam before being selected for the Naval Test Pilot School. In total, he has logged over 6,000 hours in 38 different kinds of aircraft. Selected by NASA in 1978, he assisted with the operation of the space shuttle and became the first active duty Army officer to fly in space. He flew on STS-41B and STS-51J, performing nearly 6-hour EVA in the famed Manned Maneuvering Unit. After his NASA career, Mr. Stewart led the U.S. Army Strategic Defense Command before being assigned to Director of Plans for the U.S. Space Command. So, ladies and gentlemen, I hope you will join me in giving a warm welcome to Mr. Robert Stewart.
So this is the crest of a school that says School for Aviation for Adults. Because literally they tell you when you go here, go fly that one. If you can't get it started, ask the crew chief and then go fly it. So this is an adult flight school here that teaches you how to fly aircraft that aren't quite housebroken yet, that will try to assassinate you as soon as they can as part of the test program. Well, these are a few of the helicopters that I've flown. This was a four machine competition. The top two helicopters you see there were for the armed helicopter. The second two machines down there are for the utility helicopter. The attack helicopter is what we call a gunship. The utility helicopter is what we call a slick, down at the bottom. Now, when you're a test pilot and you get assigned to a program like this, since I was the only test pilot at the time that had actually flown helicopters in combat, I was given the books on both of these helicopters, the top two helicopters. It scared me when I looked at the books. How can a sane engineer do things like this? First of all, let's look at the top helicopter. This is the way the Apache looked in the early days. Now, an experimental test pilot's job is to fly this machine, find out what's wrong with it, and maybe even help them decide how to fix it up there. Now, you know, when I first got this picture, it was a line drawing in a book, and I look at this high T-tail, and that has me concerned. Why do you think that's so? Y'all know anything about helicopters? When I look at this thing, my mind pictures the flow field coming through the main rotor, and I picture it as I'm moving forward, and I see that flow impinging on that high T-tail. And I'm saying, what sane engineer would put the tail way up there and make it non-programmable? Now, it's not that I'm so smart, but I do read the trade publications, and if you look at the bottom two helicopters, their tail is mounted way down low, and look at it, it's programmable. It does things, and it keeps that flow field from impinging and making the helicopter stick its nose straight up into the air so that you're flying it almost like a railroad locomotive in the old days, you know, with your head hanging out the side of that thing. As a matter of fact, I looked at that tail rotor. Now, one thing I see as a test pilot is I see the ground down here, and I see this plane up here at the top. To me, that says, holy smokes, that's a tunnel, isn't it? That's a tunnel. It's got this huge tail up there. It's not programmable. I've got a big propeller in a tunnel, and I'm worried about whether I can keep control of this thing. Because that helicopter blade back there is going, that tail rotor blade, is going into what we call a vortex ring state. Now that's a dangerous type thing going up there. Plus I look at the drawings inside it. It has got a big fan in the middle of the tail rotor drive shaft. I don't like anything in the middle of my tail rotor drive shaft. If If that thing comes apart, which it probably will, because that fan is rotating in a dirty environment, I'm going to be in a heap of trouble. I look at the canopy where the pilot's sitting. The pilot sits in the back seat in an Apache, as you might know. Look at how close that rotor is to the canopy. As a matter of fact, it did have a canopy strike as Hughes was testing it down there at Carlsbad, California. So when I get the aircraft at Edwards Air Force Base, Hughes is worried about that canopy strike. And they begin to say, okay, we can get a laser sensor and we can put it on that little miniature wing there, and it's going to fire a laser back up. I'm going to put a reflector on the main rotor blade, and it's going to reflect back, and I'm going to get a good estimate of where the blade is in relation to the canopy. And they're working on this thing, spending tons and tons of money. I said, well, what I think I'll do is I'll go down to the hardware store here and get me a dowel rod and some tape. So I cut different lengths of dowel rod, taped them alongside the canopy as point of closest approach, and that was my flight test instrumentation for canopy clearance. It was a machine that had tons and tons of potential and some really, really bad problems that needed to be worked out. But I was confident that it could. Now, its competitor was that helicopter just below it. This was the UAH 63, which I flew as a short control test. Chuck Thomas and I, who flew the thing in the test, swapped helicopters for the last hour or two of the test program so we could get a look at each other's helicopter. But I cheated a little bit because I was flying an AH-1R program at Bell Helicopter, and I got a chance to look at this thing with its skin stripped off, and I got to see what's inside there. And that's why I said to Colonel Boyle, our commander at the time, I want to fly the Hughes, not the Bell. Why did I say that? Well, the thing mechanically had a control mixer system in the middle of it. Now, this is a helicopter gunship, remember. If I get a bullet in that mixing mess in there, which looked like an explosion in a plumbing factory, the thing doesn't have a chance of flying. Its vulnerability was huge for that control mixer thing. As a matter of fact, I looked at the main rotor blade. Now, you know, main rotor blades should have decency to be about like this. The rotor blade on the UH-63 was over 1 meter wide. I'm talking a rotor blade like that. That rotor blade like that, do y'all know what produces the pitch moment on a camber airfoil? So this is a camber airfoil that I'm slinging around and around just above my head with a cord length so big that it's going to put tremendous stresses on the control links. As a matter of fact, such tremendous stresses that the engineers put 2 pitch change control links on that thing. And it's a good thing they did because Chuck Thomas broke one while he was in the test program there. So you look at that thing and you say, there is no way in hell that this thing can win this competition. Except there was one problem, and that is some of the Army higher-ups, I'm talking retired generals now, went to work for Bell Helicopter, and they wanted a Bell helicopter. It was a really, really hard sell to get them to switch over to the Hughes, mainly because the Army loved working with Bell management and hated working with Hughes management. Now, I agree with them on that, but I don't agree with them on the helicopter itself. Down here with the helicopter labeled UH-60, first of all, look at the difference in the rotor height over there. The Army put out a specification that says this helicopter must be air transportable. That's why the rotors were so close to the cockpit in everything except the UH-60. But what what they didn't count on was air transportability would cause very severe vibration problems in the airframe. The rotor blade going so close to the top would create a tremendous vibration, and as a matter of fact, on the UH-61, I had trouble counting the instruments, much less reading them. The bell wasn't too bad in that regard, but it was something that you didn't want to deal with that control mixer. The UH-60, Sikorsky, had a very innovative solution to the stability augmentation system, the SAS. You might hear people talk about SAS. That's what it is. It's a stability augmentation system. And they decided that, hey, we're modern. We want to get away from electronics that can be interfered with. And so we will put a fluidic SAS on this thing. You know, fluidic computer just has channels and little chambers and things that cause fluids to swirl. And they're really quite handy, except if you're on a helicopter. Now, think of this. What do you think the fluid flow through that SAS is dependent on? Primarily viscosity of the fluid. Now, if I'm flying this UH-60 at Fort Drum, New York in the middle of the wintertime, where I'm freezing to death just walking out to the airplane, versus flying it at Yuma, Arizona in the summertime, where I can fry eggs on the pavement out there, it's a completely different helicopter. So they decided that they needed an electronic SAS. They sent me to Sikorsky at Stratford, Connecticut, to do this development work. It was a wonderful test program because I am an instructor pilot in the UH-60. I have never started the thing. I'd have to get my student to start it for me when I went out there to get him to check out in it. The reason is that at Sikorsky or a manufacturer's plant, the pilot, Joe Cool, doesn't do menial things like a pre-flight inspection, like starting the helicopter. So when I walked out to the helicopter in the morning with my helmet under my arms, the thing is already sitting there running, and I go fly it and I come back. I don't shut it down, I just get out and walk away from it. What a great program that was. We discovered a lot of things. Look at that T-tail down there. You see how it's coming down like that? That's a hover position for that T-tail, or for that, lower tail. Meaning that as I fly out in there and I'm going through translational lift and my flow field is bending down towards that tail, the angle of attack on the tail goes straight up. It doesn't interfere. It doesn't stick my nose up in the air like that high T-tail on the UH-64 there. But there is a problem with something like that. We had, I guess it was 2 helicopters that we lost. Because as they were flying along, one of them flew too close to a commercial radio station. The tail on that helicopter went down like you see it there in that picture, which obviously made the helicopter pitch forward all the way inverted. Everybody dies. So the Army decided the electronic flight control was the way to go, in spite of the fact that you had to put out a note under it, don't fly close to commercial radio stations. The UH-61 down there below was a Boeing thing, had a lot of wonderful features on it. It was a rigid rotor. The first time the Army had flown a rigid rotor. Control power was out of this world. The tail was in the right spot. As a matter of fact, with the tail down there, you could use it as a work platform to work on the tail rotor. But look where the rotor is, how close it is to the canopy. When I went down to Wilmington, Delaware to test this thing, I had a Boeing test pilot with me. He put me in the seat and he showed me how smooth it was at a hover. And then he said, "Okay, sir, it's yours." And as soon as he did that, I called Wilmington Tower. This is Boeing so-and-so request a self-departure. Wait a minute, you can't do that. Look at how smooth it is in a hover. Yeah, but you've already shown me that. I don't need to see it again. When I went out to the south there, it was smooth as silk. At 100 knots, at 110 knots, it was like driving down a railroad track. The vibrations were so bad that I couldn't count the instruments, much less read them. So my flight test report, when I went back to the Boeing higher ups, was I just stood at the podium and went. On the way out, one of their test pilots took me by the sleeve and they said, "Bob, we told him not to bring you here. We're sorry we wasted your time. But we've told him everything that you told him about this machine." The reason that I saw that control mixer on the UH-63 was that I was at the Boeing Corporation to flying a test program on the AH-1R. As far as I know, it was a test bed for the AH-1S and was the only one ever made. My flight test report on this one was very short and sweet. I mean, I've flown not all that much time in a Cobra, but it flew like every other Cobra I'd ever been in. So I just told him, "Golly, you know, the red light on torque gauge is in a different spot on that thing." The OV-1 down there, the Mohawk, did not have an angle of attack sensor. A lot of people hurt themselves in the Mohawk because they didn't really know what the angle of attack was. So I got the Mohawk fitted with an angle of attack sensor. And my job was to go up and fly in all configurations to calibrate the angle of attack sensor. Now, I'm a cheater. I know that if I stall this airplane, and that's what I was looking for, a stall point on the angle of attack, with the critical engine out, what's it going to do? It's going to spin. And the Army said, "You can't spin a Mohawk. It will break the tails off when you try to recover it." Now, that's the Army's theory. When I was at Pax River, I flew with a guy named Walter Honor. Walt Honor was a guy whose claim to fame was he had most out-of-control flight time in the Navy. So I had spun this thing in every conceivable situation before before I went to do this angle of attack program. You ever heard of P-factor? P-factor is primarily with tail dragger airplanes, and that's what causes it to want to go off to the left. Well, in this aircraft, with the critical engine, which in almost every situation that I know of in an American twin-engine airplane, the critical engine is the left engine. Critical engine is defined as the one that, if it fails, gives you the most trouble to deal with. And thus, sure enough, when we did this, installed it with the critical engine failed. The right engine climbed up over the left, and here we go, spinning upside down across the Mojave Desert there. Except Walt told me a secret, and I want those of you that are in the Aero Club to remember this secret. As a matter of fact, I'd like you to try it out the next time you take an airplane and you go spinning it. Try recovery, not the way that your instructor is going to tell you, which is opposite rudder, nose down. Try pro spin aileron. Now, if you got a really sophisticated airplane, or one that is not quite housebroken, sometimes you don't even know which way it's spinning. If you just look out at the earth, it's just one blur to you. The one thing that you can do is look at your turn and slip indicator. The turning slip indicator's got this nice needle that points this way. If it's turning, it'll point the direction of the turn. That is your cue. Aileron towards the spin. And I've never flown an aircraft yet that didn't recover with that control system. So the next time you fly, you go spinning, you're looking for your flight instructor's rating, go spinning that thing, try that pro spin recovery technique. The next aircraft down, the U-21, it's a Beach King Air without the air conditioning system in it. The Army pays extra for making things more uncomfortable, I think they do. We flew this thing up around Seattle, Washington, trying to get ice on it. The Air Force flight, the weather people thought we were crazy when we go and said, tell me where the worst weather you got is. No, it's not that. So we ultimately got up there and we found ice in exactly the wrong place, which was over the Cascade Mountain Range, right where I don't want to find ice. But we flew it, we got through with it. We told people you're using the anti-icers wrong. The anti-ice system on this airplane is inflatable rubber boots on the leading edge of the wing. Now, typically, pilots were getting into icing conditions. They would turn on the anti-ice boots and they would start pulsing and they would leave them there. And they worked fine up until you developed this thin layer of ice outside of a boot flexing area. And that's why you built up this ton of ice on this airplane, and a couple of them crashed with killing everybody on board because they were too damn heavy. We just told them, hey, change the way you fly in the ice. Do not turn your anti-icing boots on until you build ice, and then turn it on and break that ice off. Wonderful, fun programs that you get to do this. That fourth airplane down there, the T-28, we had a T-28 for airspeed calibration, and it was just a joy. As a matter of fact, my last flight in an Army airplane, I flew this thing from West Palm Beach, Florida to Edwards Air Force Base, no radios. Oh, it was wonderful. I'd sit there with the canopy pushed back and smelling that burning oil coming by and pretending I was flying a SPAD during World War I. You guys shouldn't have let me do that. I forgot which pocket I put this thing in. Flying fixed-wing airplane is something else. That top airplane is just, it's a sweetheart. It's a T-38, and I was stuck flying that as the only airplane I was flying for 8.5 years. It's just like being stuck. Well, somebody tells you can't drive anything but your Lamborghini for the next 8 years. F-104 was below that. My job when I got to NASA, since I had a pretty good reputation as an experimental test pilot, they said, we want you to monitor the development of the Space Shuttle's entry flight control. Talk a little bit about that later on here. Well, to do that, I'm flying several different kinds of airplanes. I'm flying this T-38 instead of just driving it cross-country to do my job. I got to fly Space Shuttle approaches in the T-38. You can do that by putting the main landing gear down, the speed brakes out, and flaps down. But, you know, I got tired of doing that, as much fun as it was, and I went out to Dryden Flight Research Center, and I said, you know, my job is developing the entry flight control. I have flown the F-104 in simulated space shuttle approaches. Can I fly yours? You want to fly my F-104? Yeah, it's not that much different than a T-38. So, yeah, they let me fly the F-104, but the reason that I wanted to fly the F-104 is that I am a con artist. You see that little smaller picture there? That blackbird? We had 3 of them. We had an SR, we had a trainer version of the SR-71, and we had a YF-12. I wanted to fly them in the worst way, as you can imagine. Actually, actually, you know, it would have been fun because the guys I've talked to that do fly the SR say it's a real sweetheart in traffic pattern. I said, that's all I want to do. I don't want to go high and fast. I just want to fly in the traffic pattern. Space shuttle. Now, I know that that thing is not going to be capable of doing the space shuttle approach because it doesn't have flaps. Do y'all know that? It doesn't have speed brakes. Do y'all know that? Why would you want a Mach 3 airplane and waste your time putting speed brakes on it? You want to go fast. Actually, it's quite a nice airplane. I understand that up around Mach 3 it can be a bit of a bitch. But down slow in the traffic pattern is great. The STA Grumman Gulfstream 2, got to fly that approach and landing test. Not a whole lot of time in it. More time as the death pilot. This airplane is so expensive, it's so extensively modified to make a commercial airplane fly like a space shuttle. Now you can look at it, that's not a normal configuration. It's got its main gear down, but its nose gear is still retracted. There's two big flat panels down there by the main gear to create enough drag to make it mimic a space shuttle's approach and landing configuration. A wonderful thing just to get to fly. Being a test pilot, it's almost obligatory that if you get a chance to fly something weird, you take that chance. You want to do that because that's what you've been trained to do. Well, Jackson, Mississippi, one night Ron McNair was at this bar and he ran into the blimp pilots. He said, you know, I got a guy that would love to fly your blimp. Can he go with you tomorrow? Bless Ron's heart, we both went with him, and I got to fly the Goodyear blimp. It's, by the way, it's like riding a whale. It's just a wonderful airplane. Rules, and these rules are as good as gold on flying your airplane in your aero club as they were in doing experimental test work. Know your airplane. Listen to what your airplane is telling you. Just because you read the manual and you know what its straight ahead clean stall configuration is and the airspeed that it's going to stall, doesn't mean that you know what it's going to do in a 56-degree left bank spiraling approach and turn situation. But the airplane knows. The airplane knows, and it's going to tell you. It's going to shake a little bit. It's going to do something to tell you that, hey, man, we're going to do something weird unless you get out of this situation. Listen to what your airplane is saying. You don't need a book. I don't know. You know, one of my jobs was to fly the airplane long enough to create all those charts in it to tell you how fast it's going to go, what its stall speed is, what all this stuff is. But the airplane knows. Listen to it. Learn how to read the language that it's telling you. Certain things are counterintuitive. The pitot heater. You know what a pitot heater is? It's that little coil of wire in your pitot tube that keeps the ice melted out of it. Doesn't sound like it could kill you, does it? Well, it has killed somewhere around 600 or 700 people because what happens is the pilot forgets to flip this little switch, beep, pitot heater on, before he takes off. And he climbs up into the clouds. And the clouds are right at that temperature where it likes to build up ice. So without pitot heat, the ice starts building up in the pitot tube. Not in the static port, in the pitot tube. It seals up. It traps whatever pressure is in the ram air side of that pitot tube. Static port is still free. As it climbs up, static port difference between the static and dynamic ports on the airspeed system begin to show you accelerating because your ram air is still high, your static pressure is going down. And then the pilot looks at it and says, man, airplane is going really fast. I better slow it down, because he's looking at the Mach meter, the airspeed indicator. So he pulls the nose up to slow the airplane down, except it doesn't slow down. It keeps going, and the pilot says, what is going on here? And I'll pull up more. There's Buffett. Buffett, what's Buffett tell me? That's Mach Buffett. For goodness sakes, we're near Mach 1. It's going to shake itself apart. Hold that stick back there. The airplane is stalled. And 30,000 feet later, it impacts the ground. Everybody dies because somebody forgot to turn on that fuel heat. I know this because I was flying a T-38 climbing out of El Paso on the way to California one day, and I had this exact scenario happen to me. And I'm looking down there, and the first thing I say was, hey, I got this airplane 10 degrees nose up. It's on cruise power. No, this airplane can't go supersonic at cruise power. Oh, dummy, you forgot to turn on the pitot heat. But somewhere between 600 and 700 people died because the pilot did not recognize that failure. Engine out checklist. You go, even the airlines these days are teaching the pilot, something goes wrong, you get the checklist out and you follow the procedures and everything's copacetic unless you're in an L-1011 taking off out of Chicago O'Hare one fine morning and the pilot lost an engine. So he picks up his checklist and he goes to engine out procedure. The step number 1 is lower the nose until the airplane hits its best single engine rate or climb speed, and then gently climb the airplane out. And that works for a loss of engine power. What this pilot had was the engine completely fell off of the airplane. And when it fell off of the airplane, it took the hydraulic system on one side of the wing, I think it was the right side wing, that it took those the hydraulic system out on that side. And when it did that, the flaps retracted. The slats came in on one side, not on the other. That wing that's lifting right now climbs over the top. We're about 150, 200 feet above the ground. Everybody dies. The pilot did everything right, except the procedure wasn't written for the failure that he had. You're allowed to find this even in flying small airplanes, particularly if you get to fly in airplanes that are multi-engine. And that's what everybody wants to do. They want to get their single engine land record, and then you go right into the multi-engine land, which you shouldn't do. Once you get your single engine certification, go for instruments. Instruments will save your life. Having 2 engines, maybe not so much. Y'all remember that airplane in Washington, D.C. It crashed? I think it was a 737. It crashed into a bridge. Everybody died. You know, I get tired of saying this refrain. And then everybody dies because somebody made a mistake. Not wise to fly through the bridge. Now, why did he fly through the bridge? Because his company told him that to increase the engine lifetime, you do not fly above a certain engine pressure ratio. So this pilot was flying right at engine at the perfect EPR, flew it right into that bridge. Now let me tell you, if I have the choice of keeping that engine at the right EPR or hitting that bridge, I'm going to bend those throttles around the leading edge of the quadrant. And the hell with what the management thinks about that. Not right. Do not be a slave to what some ground pounder tells you have to do. If you're going to kill yourself, it's best not to do that. Situational awareness. Everybody loves Sully. They made a movie out of him. And he did a fantastic job landing that airplane in the middle of the Hudson River. But wouldn't it have been better not to hit the flock of geese in the first place? Somebody in that cockpit needs to be looking outside. Now, I know that Sully, if he's looking inside, he's busier than a one-armed paper hanger trying to fly out of that New York control area. But you don't want to fly through the flock of geese. So situational awareness. Be aware that there are things that can cause you to deviate radically from the procedures. Now, all of that led to this. I loved it. Mark Marietta Man Maneuvering Unit. I mentioned to you briefly that I gave my favorite helicopter, the best helicopter I have ever flown, a handling qualities rating of 10 in sideward flight, because that's the way we simulate hovering in a crosswind. This thing is a 1. The only thing I've ever given a 1 to, but I could literally thread a needle with this thing. It was a sweetheart. And you can see this thing here that I'm flying, if you just go out to the Space and Rocket Center, and you get to talk to fascinating people out there. I mean, I have met legends out there. Now, unfortunately, the legends are dying. When I was here working in President Reagan's Strategic Defense Initiative, back a long time ago when I was a soldier, I met half of the German rocket team in there. I sat there at my desk as the general, but I was like a little boy as they were telling me tales about what happened during World War II, what happened with their V-2 rocket, how did they get around this in their V-2 rocket. You see, because there's no point in me making the same mistake. I can learn from their mistakes. And that's the way you get to be a good old pilot, is you learn from everybody else's mistakes because you won't live long enough to make them all yourself. Now, I'm going to attack here because you've been told this all your flying career, how the Bernoulli principle works, how the air goes faster over the top of the wing and not quite so fast across the bottom, and that creates a pressure differential. But that's not true. It's not true at all. It's in every textbook that's ever been written about aviation and why airplanes fly. Why do airplanes fly? The correct answer to that question is, we don't know. We've got a lot of theories, but none of them are complete. And this is, according to the Glenn Research Center's #1 incorrect theory about airplanes. This is one you'll be taught by your flight instructors. But if you look at the equations, there is nothing in the Bernoulli equation that requires equal transit time. Now somebody might tell you, well, if you didn't have equal transit time, you'd have one layer of air that's moved over and trailing another. You can't slide one whole layer of air over, can you? No, well, of course you can't, right? The thing is, you don't need to. Equal transit time is an figment of somebody's imagination. As a matter of fact, if you look at a smoke tunnel, you can have a pulsing smoke tunnel that will put out a puff of smoke, top surface and bottom surface, and you will find that the bottom layer air goes a whole lot faster than the top layer of air. Blows it away. There is no equal transit time. Flow does not meet at the trailing edge. Okay, so it doesn't explain the upwash in front of the wing. See, we draw these nice straight lines, but air does not behave like that. Air has an upwash factor in front of your wing and a downwash factor behind your wing. We're going to talk about that a little bit more. That's a very good theory on why airplanes fly. It doesn't explain tip vortices. Because because vortex strength is very important in an airplane. In order to generate the lift to support a small airplane, think Cessna 150. Then the length of the upper surface needs to be, according to the Bernoulli principle and equal transit time, about 150% as long as the lower surface. You see that red outline of a wing down there? That's a wing with 150% length, where the top surface is 150%. You ever seen an airplane with a wing like that? Well, there's something wrong there. Typical camber of a wing is 1% to 2.5%. As a matter of fact, when I was learning how to fly airplanes, I worked for a Cessna dealer, so I had access to a lot of different wings. And I decided that something doesn't sound right about this. So I took a tape measure, and I measured from the leading edge of the wing to the trailing edge of the wing, on the top surface. And then I took the wing and measured it on the bottom surface. I found there's about an inch and a half difference. Do you think that an inch and a half worth of wing is going to create enough difference in pressure to lift an airplane? Ain't going to happen. A Cessna 172 with the wing geometry that it has would have to fly 400 miles an hour to generate enough lift if the Bernoulli principle was applicable. Ask yourself, how do symmetric airfoils work? There is no difference in the length. How do airplanes fly upside down with a negative camber? How does a wing designed to lift the airplane, because we've all drawn the picture, lift your airplane in level flight, how does it pull 9 times that much lift pulling out of a supersonic or a high subsonic type? That's why that theory is Glenn Research Center's #1 incorrect theory, and it's in every book about aviation that I've ever seen. And it's strictly bullshit. This quote by Richard Feynman is one that I love. That we have written an equation does not remove from the flow of fluids its charm or its mystery or its surprises. That's why we invented the Navier-Stokes equations. Now this is the equations that we've invented right here. Now, if you solve these system of 5 or 6 or 7 partial differential equations, you can be pretty sure that you understand flying. But this scared me to death, and that's why I became an experimental test pilot, because I don't know if we've ever solved the Navier-Stokes equations. And you know, I'm talking as a guy that spent a good time cheating death in combat and the helicopter. The worst thing I've ever done, the closest I've ever come to dying, was trying to teach young kids like you how to fly a helicopter. This is something that's really, truly amazing. My wife told me that she didn't ever have to see that again, as a matter of fact. By flying aircraft that aren't housebroken, by flying solo at 1,000,000 feet altitude at 17,500 miles an hour. And none of that scared me. The Navier-Stokes equations scared me. Because see, nobody ever draws the true flow fields around an airplane. Look at this flow field up here. I've got cambered and uncambered airfoils at the top down here. The left side, generally at the top, is a cambered airfoil. The ones as we go down there, on the left side is a symmetrical airfoil, showing you the lifting surfaces. You know, everybody draws that Bernoulli thing, everybody draws this top curve, and the top bottom flat. Well, the bottom ain't flat on an airplane wing. Have you ever seen an airplane wing? The bottom is curved too, so it's got a lift factor too. That lift factor you never see drawn on your flight manuals right here. But look at that upper left surface, lower and upper surface on the left side of the slide. That's a non-cambered airfoil. You'll see that its advantage is that I go increasing angle of attack. The aerodynamic center doesn't move. It stays there. Look at those two black arrows going one up and one down. That's your lift vector. It changes because you're making the airplane climb. But the moment around the aerodynamic center doesn't occur. Because on the right side now, you look at what a real airfoil is. A real unsymmetrical airfoil. I didn't mean to say that symmetrical airfoils were unreal. But look on the side here. I've got a lower surface lift that's going down and an upper surface lift that's going up. Now, what would you say if you were in a physics class and you saw that? Well, that's a couple, isn't it? And a couple, I can create, I can draw it as a circle here, and I can move it anywhere because it doesn't matter with a couple. Look at the lift on the bottom right here. Now I've got a lower surface lift that's longer, but it's still offset from the upper surface lift. Now with that configuration, I can create a lift that will hold my airplane up, but I will also have that moment about the aerodynamics. You guys that have flown airplanes, have you had anybody explain to you the couple, the moment about the aerodynamics?
Not really, no.
Yeah.
I was told if I was asked in my check ride to explain how the airplane generates lift, the answer I was supposed to give to the examiner was the design of the airfoil facilitates lift.
That is a problem with where we're going next. Incorrect theory number 2. I love this one because I did it experimentally when I was a kid. You know, this was before they had air conditioners in cars a lot. So my dad was driving down the car, the road with the windows rolled down, and I'm sticking my arm out there. And I do this. Oh, look at this. I'm an aerodynamicist. Look at this. My hand doesn't look much like an airfoil, does it? This is really partially correct. And that's the trouble with a lot of these things. You know, there's a little bit of Bernoulli effect on incorrect theory number 1, but incorrect theory number 2, I think I'm getting pretty good here. Just having the air bounce off my hand, I'm creating a downward flow of air. But maybe that's what I really want to do. Maybe I want to create a downward flow of air. Because if I create a downward flow in a mass, then it's going to have an equal and opposite reaction somewhere. Where do you think that might be? Incorrect theory number 3. It's got a lot of the problems that Bernoulli number 1 has. Look at there, there's the free stream velocity. We all know what a Venturi tube does, except streamline is not a surface. Streamline is created by the flow, and it's true that nothing will flow across a streamline, but the streamline has no physical effect. It's just what happens. Magnus force. You ever heard of that? It's why a curved ball works. Because you see, as this tumbling sphere goes in a flow field, it will generate a force, a lift curve. What does that make you think? Maybe rotating flow fields have something to do with lift. And if you get to be really good at throwing a curveball, you can make tons of money with the Los Angeles Dodgers. notar, no tail rotor on this helicopter here, because it works by the Coanda effect, which says that a flow of a fluid will tend to stick to a surface and follow that surface as long as it can. Maybe a wing lift has something to do with the Coanda effect. Trouble with the Coanda effect is you can make an airfoil that will fly 2 or 3 times its normal lifting vector. But the Coanda effect has to be supplied externally. In the no-tail rotor helicopter, it's supplied by pressurizing that tail boom. And that tail boom you can see with that red arrow on the back, on the far right side, that's going to be my directional control. That's going to be the vent that opens and closes as I work the anti-torque rotors. And the Coanda effect is going to take place on the tail boom itself. And it's going to counteract that torque that the main rotor is producing. But it has to be supplied externally. It has to have something to pump air to generate that flow field that the Coanda effect depends on. Does not occur naturally. By the way, that was a wonderful flying machine, because in spite of the fact that it was a little bit of, pardon my language, a little bit of a bitch, of trying to keep it under control back there because it's not strong. I didn't have to worry about sticking my tail rotor into a tree. I hate when that happens. You know, airplanes don't fly good with the tail rotors stuck in trees. The Kutta-Joukowsky theorem. This is my favorite because it explains so much. That picture at the top there is a camber airfoil in ideal flow, and this is what your air looks like. We won't worry about the fact that your velocity has to be infinite around that sharp trailing edge. We'll just ignore that for a while. Explains a lot. It explains upwash in front of the wing, because what I'm going to do is now superimpose a circulatory flow field over that ideal flow in the top, and I'll get something like in the bottom. That circulation around it is going to generate a positive lift for me, and that explains a lot of stuff. Downwash behind the wing, which is where your lift comes from, by the way. I'll see. Tip vortices. Have you ever thought of this? Have you ever landed at Nashville behind the 1011? Or some big airplane like that? What's that tower controller going to take? Watch out for wake turbulence.
Yep.
That's because the air is spilling off the end of that wing, making these tight, curled up vortices like you see in the blue side of the picture over there. So with that, I've got a nice wing up in here, but I have a bound vortex that generates that circular flow around the wing itself. That circular flow spills over to your tip vortices. So when do you think it's their most dangerous? When the airplane is going supersonic, or when it's landing? You see, because of the Kutta-Joukowsky theorem, I can generate my lift. I can say that my lift minus F is equal to rho, the air density, times the velocity of the air, times gamma, the vortex strength. Now, if airplane doesn't change weight dramatically during the landing approach, then its velocity is going to be slowed down, right? Well, that equation right there, my density is not going to change radically. My force is going to be about the same. My velocity is going to be decreasing. So that means that my gamma, my vortex strength, has to increase. And boy, does it increase to the point where it will wrap your butt around your Adam's apple The trouble with the Brigadier is I don't know how to do line integrals around a complex surface. And I don't know anybody that really does. You know, we can pretend that we do. We can write the equation, but we will never show a student how to solve those equations. Shedding vortices. That right side picture there shows you how the vortex really works. It doesn't only come around the edge of the wing. It sheds vortexes all along the ring. Now, this is something that we can remember as we look at something a little bit further down the line. The problem with the Cauchy-Joukowsky theorem is it is also wrong, because you see its existence depends on the Cauchy condition, which says that an airfoil with a thin trailing edge, how thin is thin? I don't know, will produce about itself a vortex of such strength as to move the rear stagnation point to the trailing edge. But that's as far as it goes. They say it'll happen. Why will it happen? That's why Cauchy-Joukowsky is an incomplete theorem. It just says the Cauchy condition will magically be satisfied. Trivial but correct lift theory. A wing generates lift because it shoots air downward and it changes the air's velocity as it goes down. It's flying along linearly through an atmosphere. There's going to be a lot of mass of air that it accelerates downward. And look at that's one of my favorite equations in physics. Thrust is equal to m dot delta v. This is the front half of F is equal to ma, because what Isaac Newton really said was not F is equal to ma, it's F is equal to time rate of change of momentum. So that's m dot delta v plus ma. And there's your other end of that equation. It's the thrust equation for a rocket motor, propeller thrust equations, outboard motor thrust equations, helicopter rotor thrust equations, and I think you're beginning to get the picture. Force is generated by changing the velocity of a mass. Pure and simple. Anybody tries to tell you that they can make a rocket engine that doesn't use fuel, he said you're going to have to use the same amount of fuel, of mass that you can throw out the back end of a rocket at a very high velocity if you're going to get any thrust. This is how it works. This aircraft is climbing out of a fog bank. Its velocity, the downward velocity that the wing generates, is forming a canyon. Look at that cute little wingtip boarding sticking outside of the canyon. And it affects what you do every time you land at a big airport, because that's why the controller is telling you, watch out for wake turbulence. Now, I've used the terms right and wrong a lot here, but you have to understand that wrong is a relative thing. We like to think that something is either right or wrong. It's not true. It's wrong to say 2 plus 2 is equal to 3. Everybody knows that. But 2 plus 2 equals 3.999999 is also wrong. But you can understand that it's not near as wrong as 2 plus 2 equals 3. As a matter of fact, with the old computers, we used to get this sort of thing all the time. 2 plus 2 equals 3.9999 until it ran out of spaces to write nines over there. Anytime you use pi, and if you're in the engineering department, you're going to use pi quite a bit. Your answer is wrong, because pi is an infinite non-repeating decimal fraction. But if you're in an engineering department, you can say, yeah, well, we're wrong, but we're pretty darn close. Let's talk about practical Would y'all like to take a break, or do you have any questions? Okay. We're going to talk about the way you really design an airplane. Not with a bunch of equations and things that your professor's going to write on the bulletin board and they're going to wrap around the room about 2 or 3 times. We design airplanes because the designer likes that kind of airplane. He's built 3 or 4 airplanes like that before. So if he builds another one like that, chances are it's going to fly pretty good. He's going to go to a book and he's going to look up the airfoil that he wants. There's a lot of things to be considered about this airfoil. Do I want a wet wing or a dry wing? Can I build a cambered airfoil that fits my design concept? I used to work for a Cessna dealer. It's the way I worked my way to get my pilot's license. Look at that top wing up there. Low wing, Piper. Airplanes, all low wing. Over here on the other side, Cessna, high wing. Excuse me, our sales pitch one year was, have you ever seen a low wing bird? So therefore, God's design is probably best doing that. There are many different reasons that you build an air wing like this. For instance, the inverted gull wing. Everybody knows that's a Corsair. You look at why is the Corsair the only thing that you've seen with an inverted gull wing? Has nothing to do with aerodynamics. It's an inverted gull wing because I'm mounting my landing gear at the vortex of that gull wing, and it will put my nose of my airplane much higher up in the air as it lands, because I'm going to put a big engine on that thing, and that big engine is going to twirl a big prop, and I don't want that prop digging holes in the carrier deck. So it's not an aerodynamic reason at all for the inverted gull wing. Dihedral, you'll hear the term. In the stability derivatives term, dihedral is CL beta. C, big coefficient. L, rolling moment. Beta, rolling moment due to size. Now I'm going to show you an airplane that entire flight control system is to produce CL beta. Well, that's the way you look at the front. Now let's look at the top end, the planform design. Obviously, the straight wing down here at the bottom, on the left side, is easy to make. I just use the same cross section all the way down there, and I either staple some metal on top of it, or I put some dope and fabric over it. It's very easy, quick thing to make. Elliptical wing is a wonderful wing. It produces elliptical lift distribution all the way across, which cuts your induced drag remarkably. The only airplane I've ever really seen that had a design like this was the Supermarine Spitfire. And that turned out to be a problem for them, because hold your finger up there and block off that tip. That changed your visibility, changed the look of that wing dramatically, didn't it? Well, the Brits ran out of ways to produce that tip cap. That, by the way, is a tip cap out there. They couldn't make enough of them to support the Normandy landing. So they started flying the Spitfires without that tip cap. And the gunners on the ships that they were flying over did not recognize that it was a friendly airplane. A lot of Spitfires shot down on D-Day because they didn't have enough material to make the tip caps for the Spitfire. And the other wing, tapered wing, is, you know what, we see a lot of that. If you go out to see that could just as well be a Cessna 150 there. Because of the wing taper ratio is a factor that the wing designer is going to look into, whether he needs to taper it or not. Swept back, go fast supersonically. Delta wing, delta wing's an interesting thing. It's been used in a lot of different places. Look at this collection of airplanes. I've got some straight delta with a broken delta at the top. That's a Saab Viggen, by the way. I think this is a French airplane. The second and third one's down. Don't hold me to this design, but you can see I've got a delta wing airplane. Matter of fact, it's a little broken the other way than that top broken delta wing. I've got a delta wing with a canard down there. Now, when I went to airplane school, people told me that canards were unstable. They were not really good for airplanes. And this, well, an airless student named Bert Bertan said, that's bullshit. All I got to do is make the forward wing with a shallower lift curve slope than the back wing and make it stall first. So you design a set of wings, then do that, and the very Viggen has been a wonderful airplane for private pilots. There's my Spitfire, the second silhouette, and the third aircraft down there is an F-117. It is an airplane designed by an electrical engineer. Oh well, it worked. It worked. Why do I always talk about sweep back on the wings? Why not sweep forward? The angles have changed. What I'm looking at is the flow going perpendicular to the wing chord across it. And if I sweep it forward, there's only one problem with the swept forward wing, and that is the torque on the tip of that wing makes it impractical to use. This, by the way, is the Arado bomber that the Germans used. It flew in 1939, for goodness sakes. It never made it into the production because the wing tip tended to twist itself off. T-30H down in, oh, this is a wonderful airplane. It's bare bones airplane. You have to fly it every minute you're sitting in the cockpit. You can't turn on the autopilot because there ain't no autopilot. I was stuck for 8.5 years. For 1,200 hours, this is the only airplane I could fly. Throw me in that briar patch. You got a variable sweep on this wing at the top. It's called I forgot what it's called right now. Anyway, there's only been one airplane ever built that I know of that did it. It's a British bomber. Standard configuration down there at the bottom, see 115, I think. Now, why are all these wings put on these airplanes? A lot of this is going to be, believe it or not, a designer liked it. You're going to see a lot of things that beg description other than the fact that the designer liked it. That airplane at the bottom was a Horton. This was an experimental airplane of Germany during World War II and was their candidate to expand its size to a ship that could bomb New York. And if Werner Heisenberg had invented an atomic bomb and they had developed the Horton bomber that was capable of delivering it to New York, wouldn't have needed to be two. We probably wouldn't have gone to the moon. I have discovered one fundamental fact about aerodynamics. A pretty airplane will fly better than a not pretty airplane. And the Mustang is a pretty airplane. But do you know why that scoop is underneath the belly? That's an oil cooler. Anything wrong with putting an oil cooler in an airplane? A bullet through that oil cooler and the airplane's down. I mean, your engine is going to seize very quickly, so that is a very vulnerable spot. Not just the cooler itself, but the oil system to cool the engine is in a very vulnerable spot. It's a beautiful airplane look at that from the front view here. It's so slim. It's gorgeous. It can fly very fast. But there was a German designer named Kurt Tank that said, yeah, you can't put a radial engine on a fighter airplane. It'll slow it down too much. So Kurt Tank went ahead and put a radial engine on a fighter airplane. This is the Focke-Wulf 190. It's my favorite airplane. I'll just be brutally frank with you. It's my favorite airplane because Kurt Tank designed every bit of this airplane with one thing in mind: how to defeat that Mustang. And the Mustang drivers called it the Butcher Bird because it was so good at what it does. You see, I can't put a big old radial engine on the front as long as I put the cowling on fairly tight. Its drag is not going to be that bad if it's tightly cowled. But if it's tightly cowled, how am I going to get it to cool? Well, I'm going to take a little bitty tiny propeller and I'm going to stick it on the drive shaft behind that big propeller that's driving the airplane, and that little bitty propeller will keep the radial engine cool on the front. I'll just have to admit, this airplane is almost the prettiest airplane I've ever seen, except this one. That, in my humble opinion, and of a lot of other people, is the most beautiful airplane ever to take to the sky. Do you see Kelly Johnson's handwork in it? I do. Kelly Johnson was a guy that he builds a very successful airplane, like a very successful spy plane, maybe a U-2. And you say, okay, Kelly, I need one that will perform better than the U-2 that you've got now. You expect Kelly to come up with a longer winged, longer fuselage U-2. He didn't. He came up with the SR-71. Start from the beginning. Kelly Johnson is an original, a genius. Getting close to the end here now. Space shuttle, a big delta wing airplane. Why a big delta wing? Well, NASA had a design for a straight wing shuttle. The shuttle wing was a very much smaller machine, but the wing stuck straight out to the side because I want a lot of drag on this machine anyway. I don't have engines on the space shuttle. I have to have all of the energy that I'm going to have when I do the deorbit burn. And I've got to distribute that energy over the entire trajectory to land on an airfield. Except my airfield is not standing still. My airfield is traveling about 800 knots crossways from my field. So the delta wing made a good compromise because I can bank the airplane and it will chase that airfield that it needs to land at. Now obviously I don't want to keep in one bank angle all the time because I'm destroying all of my energy on one configuration, and if I have a problem I'm going to die. That's a common thread with these sophisticated airplanes. I'm going to die. So I'll build this big, huge delta wing, and if I'm going to fly up where the air is pretty thin, in fact, the air is almost imaginary, up where I start using these huge ailerons. They're actually elevons. They're a combination of elevator and elevators and ailerons. Ailerons. I knew there was one control out there. I was forgetting. Look at the view from the bottom up there. It's got landing gear. Landing gear don't do you any good if they're stuck up inside the airplane. You got to get them out into the God's firmament pretty soon, so you got to have doors. And if you have doors, you can have leaks. And if you have leaks, the tires can go flat inside there. engineers begin to think, what are we going to do if we get a flat tire and there's no quad A we can call, no AAA that I call to get it fixed? Why don't we put the wings on the top, or the landing gear on the top of the wings? Seriously, they suggested, in order to avoid leakage around this landing gear door, to put the landing gear on the top of the wing, and we ended upside down. People seriously think of things like that. Look at the color scheme on it. It's black on the bottom, and it's white on the top. Why? Some engineer decided that was a cool color scheme? No. We paint things white that we want to keep from getting hot, and we make things black that are going to get hot, and we can't help it anyway, because black is a great radiator. You ever wondered why the radiator in your car is always black? Even back during the old days, during the Apollo program, the cooling mechanism for the reentry of the Apollo capsule was not burning off, not gas percolating out and carrying away heat. It was the fact that the ablative heat shield turned to black. And when it turned to black, it became a really good radiator. Now, we've got a funny looking airplane here that's going to have to do the big trick of coming from Mach 25 to Mach 0, unlike any other airplane that's ever flown. And it's got to do it without a window. How do we make it do that? Well, first of all, we found out that there were a lot of things that conventional airplanes do that we are not able to do with the space shuttle because we don't know what will happen. What I want to do is I'm going to come into the atmosphere at close to 18,000 miles an hour because I'm going 17.5 in orbit, and once I do the deorbit burn, I'm going to start to falling, and as I start to fall, I'm going to start speeding up. So as I come in, I'm actually a little bit shy of 18,000 miles an hour. Things are getting really, really high out there. In order to keep from jumping out, in which case I might starve to death before I get to come down, I'm going to dump that lift by turning it sideways. How am I going to roll it? Remember we talked about CL beta a while ago. I'm going to use as my primary control variable the dihedral effect of the airplane. Now that I'm showing you here the vectors that 1 degree of control activity would produce. So obviously my 1 degree of beta right here overrides everything. As a matter of fact, I'm up here at 1/10 of a degree of beta. I'm flying this airplane and it is sensitive to 1/10 of a degree of side slipping. My job here in this flight control system is to balance these vectors so that they come out to a point somewhere out in the middle of this plane that is defined by my control system offsets, my lateral shift and center of gravity. And learning how to do this, how to fly an airplane at Mach 25 and keep all these things straight were the design goal of the spaceship. Is it any wonder that we failed continuously? We'd spin, crash, and burn. Now each one of these corners that you see here with the little numbers sticking out on them are aerodynamic variation sets. Since this chart is controlled, consists of the control scatter bands. In other words, at 1 degree of side slip down there will produce a yawing moment somewhere in that lower line. And in a row, it's going to produce a moment somewhere in that upper thing. So with all these together is what I have to balance out. Now, when we started flying this thing in wind tunnels, we got these horrendous scatter bands. NASA management up here in Washington that don't have to fly this damn thing said, well, obviously there's your scatter band, so your real number is right in the middle. So we'll just build a flight control system that'll fly those real numbers. That's all we need to do. And we guys that have to get in the damn thing and fly it say, oh no. It could be anywhere in that box at any given particular time, at any given particular Mach number. We want an airplane that can fly regardless of where these control vectors are pointing. And that was our problem. I wrote a memo as we were down into verification. Verification in NASA terms is we're just looking to see if the flight control was designed to the way we designed it. If the flight software duplicated the way it was designed. And we would spin crash burn. Spin crash burn. Not one of my favorite things. With the LVAR 12, you look up there and find little 12. The little 12 on the beta and the little 12 on the other control variables constituted a variation set. And we said we wanted to fly the worst case combinations of all these variations. I'm in verification. I'm going to fly whatever I came up with, and I'm still spin crash burn scenario. So I wrote a memo. It's one of my prized, actually it's probably my prized possession. It was a Bob Stewart to John Young memo, and it said in crude terminology, inter-flight control system is dangerous, needs redesign. Or Johnny boy, you're going to kill yourself. And this was a Bob Stewart to John Young memo. Somehow, John probably inadvertently mailed it to NASA's chief engineer. So I'm sitting at my desk one day and I get a call from Walt, oh my gosh, what's his name?
Cunningham.
Who
Cunningham and Walt Cunningham. Walt Cunningham.
Yeah. What Richard said. Anyway, he attacked me. Walter is a great engineer, ex-15 guy, fine old man, but he is not schooled on how to deal with helicopter gunship pilots. He says, what do you mean writing this memo? You can't write this memo! Well, I said in my calmest, erudite voice, what part of not worth a shit did you fail to understand? Last name slipped my mind. Bam! I hear the phone sound. For some reason I still can't hear out of this ear. Oh, okay. 2 days later, I get a call from, when you're 83, you got so many names in your head. I get a call from George Abbey, my boss. And normally when George calls, since he picked all of us, and we were his boys, it was normally, Bob, I need to talk to you sometime in the next couple of days. You make an appointment with Mary and come see me. This wasn't that way. This was a Bob, get your ass over here. Well, I'm not real bright, but I do know what this is about, because I just told NASA's chief engineer to stop it. Walked over there, he kept me waiting for about 15 minutes in his front office, and Mary Lopez, she wouldn't say a word. She's sitting right this. I know that I'm about to get fired. Fortunately, I knew that before I came over there, so I brought all my data. And he came to show it to me. So I laid it down, laid it all out, showed him all the spin crash burns. Said, George, if we lose this airplane, we've lost a manned space flight forever. And George said, yeah, now I understand. So next day, George, we were like Don Quixote and Sancho Panza. Him being Don Quixote, me being Pancho Sanza. But anyway, we picked up his spear and we went jousting windmills and we got the redesign we needed. See, the thing is, as I was wasting all this time flying flight systems that I knew we were never going to fly, we discovered the right combination. It was a matter of very simply, we found out that Holly Barnes was causing all of this, so we made Holly stay on the outside of a computer simulation lab, and she forgave us for all that, by the way. And we got the right flight control. We got John and Crib back, and then we got everybody else back. But it's an indication that if you go into engineering, it ain't always easy. You find people who have their careers invested in maintaining cost, maintaining schedule, and that's what NASA headquarters exists. Sometimes I think they don't even really give a shit if the thing actually works. But us guys that have to fly, we care. First set of Army astronaut wings, and I was just so lucky to get them. Air Force and Navy astronaut wings look about the same. Take your pilot wings, whatever you got, or your air crew wings, whatever, and they will mold that little thing that's in gold there into their wings. So an Air Force pilot's going to have a gold emblem, a silver emblem like that. The Navy's going to have a gold emblem like that. But gold has a specific meaning for the astronaut office. You wear a silver pin if you're an astronaut candidate, but you haven't flown yet, and you wear a gold pin if you have flown. So that's, I would try to talk the Army into mixing those two. I was so proud to get those. I gave the first set to the Army Aviation Museum down at Fort Rockville. Oh my God. Thank you all for sitting with great patience through this. If there's one thing I want you all to take away from this thing, is listen to your airplane. You're going to go out and you're going to fly these little Aero Club airplanes, and they've been flying for 50 years. They're not going to kill you, but learn how to listen to it. Learn what it's telling you when it says, I don't like this situation, get me out of it. Because someday you might have to fly an airplane. If you're very, very lucky, you'll get to fly an airplane for which there is no book, because you will be writing that.